this talk presents Substrat, a subset-based optimization strategy for faster AutoML. Automated machine learning, AutoML, is gaining more and more traction from the data science community because they practically allow to build robust and accurate machine learning pipelines with basically no human effort. So such framework mine ML configurations that contains data preparation steps, feature engineering, model selection, and parameters tuning, and find an optimal pipeline with respect to some metrics such as accuracy, F1, precision, recall, or any other user-provided metric. Naturally, the main challenge of AutoML platforms is the time, because brute forcing the entire search space of all configuration for machine learning pipeline that includes data preparation, feature engineering, extraction, model selection, model tuning, etc. is infeasible. And also, as we noticed in this work, when the dataset itself is large, then the execution of each pipeline, even if you manage to reduce the number of considered configuration, then even so, each pipeline execution takes a lot of time. For the general problem, there are two main approaches in existing works. The first approach is search optimization and heuristics. Such approaches using techniques such as Bayesian optimization, genetic programming, and all of this to reduce somehow the configuration space and focus the solution on promising machine learning pipeline configurations. Another approach is meta-learning, where we in fact infer which configuration elements to use based on mining existing configurations that were performed on different datasets. So this is basically employing machine learning for machine learning. But different than these two types of solution, Substrat focuses on the size of the data rather than on reducing the configuration space. So we look at AutoML as a data reduction problem. The idea behind Substrat is fairly simple. So let M star be the best configuration generated by an AutoML tool A over a dataset D with a target feature Y. Then the time of M is the time it takes A to generate M star. The accuracy of M star is the output model accuracy. So the goal of Substrat is given D, A, and Y is to generate a model, let's call it M sub, such that the time of M sub is much smaller than the time it takes to produce M star, but the accuracy of the two models are fairly similar. But a decrease of more than 5% in accuracy is largely unacceptable for machine learning models, so it doesn't worth our time if the accuracy decreases a lot. The idea behind Subset is to take and compute a data subset of the full data in order to reduce AutoML computation times while retaining the output model performance. So this is simply done as follows. Given a full dataset D of size n times m, a target feature y, and an AutoML tool A, the first thing that we do is find a very small subset called D of size n times m, which is significantly smaller than the full data. We then want to employ the AutoML tool A on the small subset D and obtain an intermediate model M tag. And the last step would be to fine-tune the M tag configuration by employing a restricted process of A, not the full process, back on the original dataset D. However, the problem is when you take D, the subset, the DST-D, uniformly at random, the process is indeed several times faster, but the performance decreases significantly. So we measure the reduction of about 30% in the model accuracy when we take a subset uniformly at random compared to the full AutoML process on the full dataset D. Okay, so we cannot use any random data subset in order to reduce AutoML time, but maybe if we manage to generate a data subset that preserves some of the characteristics of the big one, then we might get better results in terms of the AutoML process. So let's define for a second what is a measure preserving data subset. Given dataset D, let R and C be the rows and column indices. So a subset, small d, is basically any subset, small r and small c, of the rows and columns of the big dataset. a dataset measure is any function f that you can employ on the full dataset or on the smallest dataset and obtain a real number. And we call a subset D a measure preserving if f of the large D roughly equals f of small d. Subset uses a dataset entropy measure, where we basically compute the entropy for each column and takes the average score. Pj here is the probability function that corresponds to the frequency of a value in the column j. So why using entropy? First of all, it's a non-parametric measure that can instantly apply to various types of distributions of columns. Also, it is widely used to characterize data distributions with known measures such as KL divergence, cost entropy, etc. And also, intuitively, if the entropy of distribution P roughly equals the entropy of Q, then a model based on P can very well predict Q. So this measure seems promising in our case, and we indeed validate this in our experimental evaluation. Unfortunately, as we select both rows and columns here, there is no easy optimization shortcut. We therefore propose GenDST, a genetic-based algorithm for finding data subset. The goal of GenDST is to find a subset that minimizes the dataset entropy difference between the full dataset and the small DST. GenDST works as follows. First, it initializes a population P0 of random DST candidates. The population is of size 3. We then modify the population in each generation using the following 3 genetic operators. The first operator is a mutation, where we decide first with a probability PRC, which corresponds to the ratio of rows to columns in the original dataset, whether to employ a row or a column mutation. We then replace one of the rows or column in each selected DST candidate in the population with a different row or column uniformly at random. The second operator is a crossover, where we want to merge 2 DST candidates, RA-CA and RB-CV. So again, with the same probability PRC, we now choose whether to perform a column or a row crossover. So if we employ a column crossover, we basically merge the 2 column indices of the 2 candidates. To do so, we choose a splitting point S between 1 and M randomly, and to generate CAB, we take the leftmost column indices from CA, and the rest M minus S are taken from the other DST candidate, CB. And to generate CBA, we take the first S column indices of B and merge them with the M minus S indices of A. So this generates 2 new DST candidates, RA with the new list CAB and RB and the new column list CBA. The last operator is called a selection, and this is used to select the best, to generate the population Pi plus 1 in the next generation. We do so using a royalty tournament selection, which means that we take a proportion alpha from the phi size of the population. So we take the alpha most promising DST candidates according to the loss function L, and we sample the rest, 1 minus alpha, with respect to the score of the other DST candidates. So this is done in every generation Pi until we reach a stopping criteria, which could be a fixed number of generation, or when the improvement in the loss function is reaching a halt. Let's now discuss how we experimentally evaluated substrate. So we did evaluate substrate on the following very common AutoML platforms: AutoSKLearn, TPOT, and H2O. We use a set of 18 different data sets of different shapes. The shapes are as follows. First, we had 8 standard data sets with up to 130K rows and 23 columns. We then used long data sets with a lot of rows, between 1 and 2 million rows, and a standard number of columns, 12. This is up to 24 million cells. We then also evaluated Substrate on high dimensional data sets with a lot of columns. So we have 5 data sets with a number of columns ranging from 123 to 309, and which results in the maximum of 11.5 million cells. And we also experimented with very wide data sets, 3 very wide data sets with up to 7K rows, but up to 11K columns. And this results in a large data set of 35 million cells. The evaluation metrics are as follows. First, we measure the time reduction, which is 1 minus the time it takes the substrate or a baseline, as we will see in the following slides, to compute the configuration M sub, divided by the time it takes the full AutoML process to generate M star. So this is the amount of time that we save when using substrate or a baseline. The other measure gauge the relative accuracy, which measure again the accuracy of the model produced by substrate, M sub, with the model generated by the full AutoML. So the higher the relative accuracy and the higher the time reduction, the better the score of a baseline. So we compared Substrate with its genetic algorithm GNDST to several baselines. The first 2 baselines are alternative optimization approach. Monte Carlo based is the simple one, which just performs a random search. So MC100 chooses 100 DSTs uniformly at random and chooses the best one, and MC100K do the same for 100K data subsets. Another more sophisticated optimization, or a meta-heuristic, is multi-armed bandit, which is a different optimization approach that balances exploration and exploitation when considering the search space of rows and columns. Another approach is a clustering-based approach where we can use and apply both on the rows and the columns. So in order to choose row representatives, we simply employ k-means clustering with size small n predefined, and then choose the cluster centers as representative. And for the columns, we can transpose the data set and do the same thing on the columns. Another approach is information gain, a common feature selection technique that we can employ only on the columns, and it chooses the best promising features with high correlation to the target column Y. So we have the baseline IG-RAND, which chooses features with IG and chooses rows using just a random search. And we also have IGKM, which chooses rows according to the clustering method and columns with the information gain. And the results are as follows, where we compare the time reduction versus the relative accuracy for each of the baselines. So the table on the right-hand side provide aggregated results for each of the AutoML platforms, AutoSKLearn, TPOT, and H2O. See that Substrate obtains the highest relative accuracy, but some of the baselines obtains better time reductions, but these baselines obtains dramatically inferior relative accuracy. On the left-hand side plot, you can see the results per dataset, and the green area symbolizes a reduction which is smaller than 5%. See this, the most points in the green area are from Substrate. So Substrate is the only approach that achieves almost consistently over 95% relative accuracy while reducing times by more than 70% of the full calculations. We also implemented a Python library for Substrate, which is available as an open source library, and we invite you to use it. Thank you very much.